Hello everybody, hope you are doing well and welcome to the FRAPCON code training course. In this course we want to learn something about the FRAPCON code, some limitation of the FRAPCON code, and after that we review the FRAPCON code structure based on the technical report of the FRAPCON code and models using this code. And after that we are gonna introduce the important input parameters used in the code and needed to be doing some simulation. And finally, and the final part of this course, we are together implementation of the case study and analysis of the results and learn something about the output of the FRAPCON and something we can get the results of the FRAPCON. First of all, we should learn something about the base of the coding of the FRAPCON. FRAPCON is abbreviation of fuel rod analysis performance at the constant steady states, and as you can see, a computer code for calculation of steady states, thermomechanical behavior of oxide fuel rods for hyperloop. FRAPCON 3 is a Fortran 90 computer code that calculates the steady state response of the light water reactor fuel rods during long-term burn-up. The code calculates the temperature, pressure, and deformation of a fuel rod as a function of time-dependent fuel rod power and coolant boundary condition. The phenomena models by the code include heat conduction through the fuel and cladding to coolant, cladding elastic and plastic deformation, fuel cladding mechanical interaction, efficient gas release from the fuel and rod internal pressure, and finally cladding oxidation. And we can extension this phenomena in the technical report, and I will discuss about that, and we can use this model for our simulation. And finally, and as I mentioned, the FRAPCON used to calculation of the fuel rod at the steady state in the reactor. And when you want to calculate the transient condition, we should use the another code, means FRAPTran. And we should know at the first of this course, FRAPCON used for the calculation of the fuel rod at the steady state before the transient condition. And when we want to use the FRAPTran, we should use the initialization file of the FRAPCON and use in the FRAPTran to calculate some accidents phenomena like the LOCA or RIA and power ramp, I don't know, and a lot of transient conditions there are in the reactor. Okay, and in this slide we should consider the application of the FRAPCON and the conclusion of this FRAPCON code to the calculation of the fuel rod analysis performance analysis at the steady state before the transient condition. Okay, any code we want to use, there are some limitations, and first of using any code, we should know about the limitation of that code. About the FRAPCON, there are some limitations. First of all, about the pellet we want to use. the current code means the FRAPCON 3, the version of the FRAPCON we use is 3, and I know some version of FRAPCON like FRAPCON 4 is developed, and I don't have any access or availability of that, and I don't have that version of FRAPCON. And in this course we use the FRAPCON 3, and FRAPCON 3 has some limitation. First, the limitation of that is related to the pellets, and the current code is limited to modeling fuel constant of U2 and PuO2 for MOX fuels, and U2 or the weight gain of the GD2O3 pellets in zirconium alloy cladding with the gas gap under light and heavy water reactor conditions. Another limitation is the thermal models of the code are based on steady state conditions and equation and calculate only radial heat flow. Another limitation is the only small cladding deformation, less than 5% strain, are meaningfully calculated by FRAPCON 3. All of the thermal and mechanical models assumed as a symmetric fuel rod with no axial constraints. The code's ability to predict cladding strain resulting from pellet cladding mechanical interaction (PCMI) has been assessed against power ramp data. FRAPCON 3 has been found to slightly over-predict cladding strain up to burn-up of about 65 gigawatt-day per ton of uranium, and in this data validated of the experimental activities in the reactor. The limited high burn-up data suggests that FRAPCON 3 may underpredict the cladding strain during power ramps at very high burn-up for the burn-up greater than 65 gigawatt-day per ton of uranium for hold times greater than 3 minutes. And we should know about the limitation, and after that use the code, any code we want to use. We should be know or notice and aware about the limitation of FRAP in any code. Like in this course we want to know about the limitation of FRAPCON. In the FRAPCON, we first of all we should know about some steps there are in the FRAPCON. For example, first of all, as you can see here, the input data are specified, and we should about some parameters that we will discuss about enter in the input data, and after complete the input data, initial condition are computed, and after that fuel rod temperature are computed. If yes, the code goes to the next step, fuel and cladding deformation are computed. If the criteria less than the 1% of the difference temperature, the code goes to the gas release, void volume, and gas pressure are computed. If this algorithm will be okay, the code goes to the next time step, and this algorithm is simplified, and we in the FRAPCON we use the perfect algorithm, and we will discuss in the technical report of the FRAPCON. The FRAPCON tree code, it calculates the interrelated effect of fuel and cladding temperature, rod internal gas pressure, fuel and cladding deformation, release of fission product gases, fuel swelling and densification, cladding thermal expansion and irradiation induced growth, cladding corrosion and hydrogen, and crud deposition for a given build-up rate as a function of time and fuel rod specific power. As you can see here, is this is the fuel rod, the schematic of the fuel rod. This region related to the fuel pellet we used, and after that we should specify the cladding, and about the fuel rod there is the planium, and this the upper planium, and this the lower planium, and in the input data of the FRAPCON we should specify some parameters related to a spring in the planium. Okay, and this is the difference temperature of the at the center of the plate, TF field center line, and after that there is the gap between the pellet and the cladding, and as you can see the temperature is decreased, and after cladding there is some oxidation because the cladding of the fuel rods is next to the coolant, and between the coolant and cladding actually there are some relationship between that. Then the oxidation happens on the cladding, and after that the oxide there is the crud deposit of on the oxide, and the FRAPCON calculate this phenomena, and we discuss about that the next step. Okay, as you can see here, this is the FRAPCON input structure, and we should complete these parameters, and here just I want to show you some parameters, and for the part of the information about the input data, we will discuss about the each parameters here. For example, DCO related to the cladding, the outside diameter, and THK CLD related to cladding thicknesses, and THK gap related to the gap thicknesses, gap between the plate and cladding. Okay, and at the right time we talk about the each parameters and use the parameters to execute or run the FRAPCON and use the input data for calculate or simulation. Here let me to talk about the technical report of the FRAPCON, and as you can see the FRAPCON 3.5, and I mentioned the computer code for calculation of the steady state thermomechanical behavior of oxide fuel rods for high burnout. Anybody wants to learn the FRAPCON or any code, first of all should study of these reports. And as you can see, this version of code is related to May 2014. Okay, briefly I want to summarize this report together and how to use the this report and study of that. First of all, as you can see here, the objectives of FRAPCON series, limitation of FRAPCON 3, and as I mentioned in these PowerPoints, report outline in relation to other reports, general modeling description, and here section related to fuel rod thermal response, fuel plate heat conduction model, planning gas temperature, stored energy, fuel rod mechanical response, and some models we use, for example, FRAPCON 1 used to efficient gas release modeling, and these will be rigid plate cladding deformation model. I think we should know about that before just using the input data or doing any simulation. We should study of this report and know about the modeling using the FRAPCON. And as you can see, the code structure, code results, we will talk about that in this course. Okay. Here the abbreviation of something. Okay, objective of FRAPCON series. You can study about the version of FRAPCON. Okay, that about the limitation of FRAPCON 3, and we talk about that. Okay, here some models used in the FRAPCON and the FRAPTRAN. Okay, about the solution of the FRAPCON. Yes, there is this simplified FRAPCON flowchart, and in this report you will learn something about the structure of the FRAPCON and something happened under the coding of the FRAPCON. Here, as you can see, related to the fuel rod temperature distribution, I talk about that in the slide about decreasing the temperature at the fuel center line temperature to the crud. And FRAPCON, as you can see, for the coolant condition, for example, FRAPCON 3 calculates bulk coolant temperature assuming a single closed coolant channel according to this equation, and you should note about that the FRAPCON not calculate the bundle of these fuel rods, just calculate the one fuel rod, single fuel rods, and calculation stands around that. About the fuel rod surface temperature, the cladding surface temperature at axial elevation is taken the new value of that. The report is very benefit for increasing your knowledge about something about the fuel rods and fuel rod behavior and something used in the base of the FRAPCON, and it's so benefits or useful or knowledge, and about the increasing our knowledge. And after that we can simulate or and analyze something about the fuel rod by FRAPCON. The finite difference approach using the FRAPCON. You can see about the mesh point layout and the input data. We use the two parameters to definition of the this mesh point for the axial or radial. Yes. Yes, it's, and you can study this report, and in this report I don't want to increase the time of this course about this information of the base of the FRAPCON. In this course we want to simulate the and you and learn something about the simulation and use the parameters and use the FRAPCON structure to extend the case study, and after that we learn about the input parameters, and after that learn about the output parameters. And as you can see here, the thermal conductivity and filtration procedures in the FRAPCON use this model for calculate the thermal conductivity. Okay, and I recommended that before doing or simulation from the FRAPCON code, study briefly about the some model used in these codes. Okay, and something about the mechanical model used. Okay. After that we will talk about the some models detail about the some models using the FRAPCON, and after that we go to the simulation or introduce the input parameters. Okay, please study this report, and for the increasing your knowledge about the something happened for the fuel rod and model in the FRAP.